Let's do another application for Lenz's law. This is called the expression for motional EMF. Now, what is motional EMF? EMF produced when there is some sort of motion involved. See, we have a uniform magnetic field, again vertically inwards, and here I have this type of wire stretched and another wire which can slide over this wire, right? So what will happen if I keep on sliding it, number of lines passing through this closed loop is going to decrease. My point is not to tell you that the lines are decreasing, it has to do with that flux is changing, and when flux is changing, what is going to happen? Induced EMF is produced in it. So this is the another example of how do you apply Lenz's law. First of all, we need a derivation and we also need a direction. So direction, let's talk about direction first. So I'll move this way just to tell you how to use the right hand rule. Motion, field, current. So I told you always start with the magnetic field which is vertically inwards, and then motion. I am moving this rod in this direction, right, with velocity v. Okay, I'm going to rub it though. So first of all, magnetic field, then motion. So direction of induced EMF is downwards in this section. That means the induced EMF or induced current is in this time it is clockwise direction, right? So direction is very clear. Applying Fleming's right hand rule, we can tell the direction of induced current is in clockwise direction. Now, expression induced EMF is given by minus d phi by dt. What is phi? Phi is BA cos of theta. Okay, I'll write it here. Phi is BA cos of theta. Theta in this direction would be 0 degree. Why? Because what is the direction of magnetic field? Vertically inwards. What is the direction of area vector? Area vector can be taken both ways, either vertically outwards or vertically inwards, right? So if you take the vertically inwards area of cross section, then it is going to be in same direction as the magnetic field, and the theta would be 0 degree. So cos 0 is 1, so you are left with B into A. So minus d upon dt, instead of phi I am writing B into A. Instead of A, let us say this length is L and the changing breadth is x. Let us also suppose that this moving element covers a small distance dx in small time interval dt. Okay, so time interval involved for covering the small distance dx is what? Dt. So first of all, minus d over dt, b, instead of area A I have to write L into x. Okay, now b and L are constants. What is left? Dx upon dt, because x is changing and we have a negative sign as well. So this small distance covered dx in small time dt is representing the velocity of this rod with which it is moving. So dx upon dt is velocity, and the dx upon dt, the velocity is in decreasing direction of magnetic field. More you decreasing direction of area actually. So minus dx upon dt is v. You can also consider it this way, that this x, that is breadth of this loop, is decreasing with the increase in velocity or with the velocity, direction of velocity, because both are vector quantity. So b into L into minus dx upon dt can be written as v, and this whole equation becomes E is equal to BLV. This is called motional EMF. So this is the expression for motional EMF.